So, good morning, everyone. So yesterday we were doing this problem where we encountered a branch point. So I have already taught you that multi-valued functions. For example, whenever I say that there's a multi-valued function, let's say z raised to power 1 over 2 or z raised to power 1 over 3 or functions like these. These functions are multi-valued functions, and indeed they have some singularity. They have singularity z equal to 0, and that particular singularity z equal to 0 is nothing but a branch point. Okay, so now when we have to do a contour integral of this type 0 to infinite x ki power p minus 1 dx upon 1 plus dx, where p lies between 0 and 1, I told you that this particular integration be replaced by this particular integration. And while making a contour, we have to keep in mind that we have to indent the curve at origin. Okay, so I have to indent a curve at origin. So what I did, I actually made a circle here. Okay, and I then made a slit construction. Is that clear? So I made a slit construction. I made a circle over here, and I tried to remove this kind of a branch point from my integral. Okay, so from my evaluation, I wanted to keep this away, and that is what is my first uh, thing that I wanted to do. Okay, now uh, as I went on, I could clearly figure out that this particular integration z ki power p minus 1 upon 1 plus z dz over c comprises of what all parts. So an elaborate discussion I've done in the previous lecture. I'm just trying to recapitulate the discussion from tomorrow itself, from yesterday class. Okay, so what we did was integral z ki power p minus 1 upon 1 plus z dz over c. So the c is this entire thing, that is from a b, then moving on to b d e f g, then from g to h, then h j a, this circle, and again. Okay, so this sort of contour. Okay, so this is my closed contour. My idea was to evacuate this kind of singularity, that is z equal to 0, from my integral of evaluation. So I wanted to remove this kind of branch point singularity. So therefore, I indented what you can say, I introduced say for example a circle, and then I made a branch cut, in principle small branch cut, or you can say a slit construction, so that my problem gets removed. Okay. Okay, and so also that by introducing this kind of slit, I have actually removed my x-axis from the evaluation. So this is where your principal part can be defined. Okay, so your principal part of the function can be defined, and your function no longer remains a multi-valued function also. So integral c z ki power p minus 1 upon 1 plus z dz, and you can clearly see that this minus 1 is a singularity here. And what sort of singularity it is? It is a simple pole. So your left hand side, you can simply find the residue and multiply with 2 pi r time. We did it yesterday. And let us see what is an integral. So on the right hand side, you can see this is AB, then you have B, D, E, F, G, and then G, H, and then H, J, A. And also remember that while moving from B, D, E, F, G, we are traversing anti-clockwise. And while moving while moving along H, J, A, we are traversing clockwise. Okay. Yesterday we already have through our rigorous calculations found that integral BDEFG would be 0, integral HJA would be 0, HJA would be 0 as epsilon tends to 0, and BDEFG integral, this would be 0 as r tends to infinite. So I think this is something that we already know. But along AB, it happens that your function is simply along the x-axis. So it is being evaluated only along the x-axis. So what you can do is you can simply write that your z equals to x. So what I did was I simply wrote z equals to x, and this is x ki power p minus 1 dx upon 1 plus x. And where I concluded the lecture was I told you just try to find this gh. Along gh, what sort of what should I write? So understand my point that after one complete revolution, while I'm along GH, I would have almost, my argument would have increased by 2 pi. So instead of x, I would write x e ki power 2 pi. Why only x? I should have wrote z or something of that sort. But I'm parallel to x-axis. So here y coordinate is 0. So you can write z into e ki power iota 2 pi. But instead of that, I have written x into e to the power iota 2 pi. Why I'm writing that? Because after one complete revolution, almost one complete revolution, you can say, because I have constructed a slit and that slit is as small as possible. So after one complete revolution, yes, initially your z was here. Now the same z after one complete revolution would be z into e to the power 2 pi, e to the power iota 2 pi minus something, and that minus something angle would be as small as possible. So I can simply write, you can write 2 pi minus del also, iota 2 pi minus del also, and del tends to 0. Overall, you can write that instead of writing z here along gh, you can write, so here I'm writing, so here it is, like on the left hand side, we've already evaluated the, I think, integral, and this is e to the power, I think I can write e to the power iota, simply pi, okay? E to the power iota pi is minus 1, isn't it? And this raised to power p minus 1. And why only iota pi? Because we are only concerned with the principal branch. Otherwise, I would have written 2n plus 1 pi. Now, because of this slit introduction, what we have done, we can only evaluate along the principal branch. So, in that principal branch, I'm doing from here to here. Okay, so I'm actually on my principal branch. Okay, so by this, I would write this, and this will be equals to 0 to infinite x raised power p minus 1 upon 1 plus x dx. And the second integral along gh would be what? Second integral along gh is I think, if I'm not wrong, r to epsilon. Okay, and I will write limit r tends to infinite and epsilon tends to 0. Okay, so I'm moving from r to epsilon. Okay, so inward. And here I would write x e to the power iota 2 pi raised power p minus 1. Then I have 1 plus x into e to the power iota 2 pi. Then along dz, I would write, I think, e to the power iota 2 pi and then dx. Is that clear? So, okay, so this is what I'm going to write. And understand my point that e to the power iota 2 pi is 1, so I'm not going to write it any further. I'll write simply 1 here. On the left hand side, I am left with this thing. This is 2 pi iota, and then you have e raised to power iota p minus 1 times pi is equal to integral 0 to infinite. And you can clearly see that this is r to epsilon. If I take this infinite, this 0, and if I take a negative here, so it will become 0 to infinite. So it will become x to the power p minus 1 upon 1 plus x. And here you have 1 minus e to the power iota. I think this is p minus 1, if I'm not wrong. And then this is 2 pi dx. Is that clear? So you're left with this. So what you can do, this is simply a constant. You can simply put it here, and this will give you this integral where we were interested initially. So we were interested in finding this integral x to the power p minus 1 upon 1 plus x dx, and which eventually comes out as 2 pi iota e to the power iota. I think this is p minus 1 pi divided by 1 minus iota e to the power iota. Okay, this is 2 pi, and then you have, I think, p minus 1. Is that clear? Okay. And what you can do is, you can simply take from here e to the power iota pi p minus 1 common, or you can simply divide this portion on the down. So what you will get, you will simply get, I think, this integral where we were interested was 2 pi iota, and you can simply place this below. So you will get, I think, there's a mistake or what, I don't know. I don't think there is a mistake till now. Anybody has any sort of problem till now? I don't think there's a mistake. You just uh, see if there's a mistake. I don't think there's a mistake. Okay. Instead, we should take a common p. Okay. So try to divide this entire equation by e to the power. I will write it here. So I'm going to divide it by e to the power minus iota. You have p minus 1 pi. ठीक है? ये divide करोगे तो ये आएगा minus e to the power iota p minus 1 pi. Okay, so just take this thing and put it in the denominator. So you'll get this, and you just take this thing common out. That is, I'll write it as e to the power. sorry, 2 pi iota divided by e की power minus iota p pi. And then what you have, I think e की power iota pi is here. So here you will get a negative. See this particular term. E की power iota pi is minus 1. So here you will get minus 1. And here it will become plus e की power iota p pi. And this is one structure that you've already seen. Or you can simply keep this here. You keep pi here and divide the entire thing by 2 pi. This entire thing, you can, if you can remember, this is nothing but this is equal to sine. So p upon sine p pi is an answer. Is that clear? So this integral reduces to p upon sine p pi. Is that clear? Anybody has any doubt till now? Bharat, is that clear to you? हाँ चलेगा सारे आगे क्या Alpna, is that clear? Bharat, is that clear?
Sir, actually, I've joined just now.
Okay, okay. So yesterday we were doing this question, and you can clearly remember that along HJ integral was zero, BDEFG was integral was zero. Okay, so we were left with only integral along AB and integral along GH. So while I was evaluating integral along AB, so what does it mean? It simply means that you are having you just have z equals to x here, and after one complete revolution, almost one complete revolution, because probably here there's a slit, so probably not one complete revolution, but close to one complete revolution. The argument of GH along GH, the points along GH, I would write it as Z into e की power iota, sorry, Z into e की power iota 2 pi, or minus some del also. I mean, because I have introduced some slit, but overall I can write that del tends to zero. So eventually I can write that any point on this line along GH can be written as Z into e की power iota 2 pi minus some del. Because see, I have introduced a slit, so I can move all along and I cannot exactly reach the same point. Otherwise, it will become a multi-valued function. So in order to say that I have just reached, I would write 2 pi minus del, and eventually I'll forget about this del. So any point on GH can be represented as Z into e की power iota 2 pi minus some del. Forget about del, del tends to 0. And because you are along GH, so I can simply write Z equal to X also. Is that clear? So what I have done on the left hand side, we've already evaluated yesterday. If you see the working that we did yesterday, so this was what we got yesterday on the left hand side. On the right hand side, we got this, and on the right hand side, we were interested in finding what would be the integral over GH. So it will be limit epsilon tends to 0 and r tends to r tends to infinity, integral r to epsilon. And instead of z, you can write x e की power iota 2 pi upon 1 plus z. Instead of z, you can write x into e की power iota 2 pi. And instead of dz, you can write e की power iota 2 pi dx. Okay. And you just try to integrate it. And while integrating, you will get what? This particular thing r to epsilon ke bajaye epsilon to r you write. Instead r to epsilon, you just write epsilon to r. Epsilon tends to 0, r tends to infinity. There will be a negative sign. So there's a negative sign. You just see this is the case. Now see, this is a constant. You can just put this constant here on the left hand side. And you're left with integral 0 to infinity x की power p minus 1 upon 1 plus x dx on the right hand side, which was the short integral behind which we were doing all these things. About which we were discussing all these things. So this was that integral. And here you will get 2 pi iota e की power iota p minus 1 pi divided by this entire thing. Just try to divide this entire thing, and you will find that this integral is given by p upon sine p pi. Don't get confused and say that sine p pi is always zero. It is not always zero. It is only zero if p is an integer. But here you can see that I wrote on the very first in this thing in the question itself, I wrote that p lies between 0 and 1. So you have to understand that whenever we encounter some branch point singularities, then we do such kind of integrals. Is that clear?
Yes, sir. Sir,
Okay.
initially in the problems when we introduced the slit, we used to
Uh,
cancel this integral, right? Saying that the both are in opposite directions.
yeah, yeah, yeah. But right now, because see, right now, okay, so that you are asking that way, okay. So actually, work etha, there we were doing what? So let us see. So the slits that we were making initially were like this. Okay, so they were simply you can say that while I was creating this kind of slit, I was simply interested in moving from here to here, here to here, here to here, here to here, all those things. Okay. Here, what is the problem? Here, I am at my origin, at my like I have to uh, I have created a slit here. I have created a slit here, and see what I have to do is I have to see how my points are evolving. How my points are evolving. So let's say uh, in this particular scenario, if I okay move along क्या कह सकते हैं? If I move along from here, so my initial points are x, and while I come all over and reach here at this particular point, I will have I think x e की power iota pi. Okay, this is one thing. Okay, now your question was ki why we actually did not look for all these things here. The answer to this probably would be here we were while we were doing these kind of things, we were interested in isolated singularities. If you clearly remember that I wrote isolated singularities while I was doing multiply connected region. I was just saying that if there are some isolated singularities, you have to do this. Okay. So when I was writing isolated singularity, I meant poles there. Okay. Now in this case, what is the problem? Here your function is actually having this kind of thing, z ki power p minus. And you should understand that this particular function is a multi-valued function. So here the singularity is a z equal to 0 is not a isolated singularity, rather it is a non-isolated singularity. So this problem differs in the sense that here we are actually not creating sort of slit construction. We are making a branch cut, you can say. Okay. So you can see that I'm making a branch cut here, and mostly I'm evacuating my origin. Okay. No doubt it seems the same way. And I was saying the same way that just make a circle here and create a slit. That particular slit was in order to evacuate my branch point from my evaluation of integral. But overall, understand that traversal of the loop here also would be the same. Like for example, here if you say uh, that your function was initially fz, and then after one complete revolution. But the point is this: you are not completing a revolution here. See, you are actually like you are coming after one this, and again you are moving back. So you have no reference point in order to know uh, how am I coming back? Like, are you getting my point? So here your function was also not sort of dependent, but here you can see that after one complete revolution, your function would change. Your function would become like e ki power iota 2 pi and some raised to power p minus 1. So here your function would change. Here your function would not change because your function is a single valued function, and we were only discussing that if your function fz is analytic throughout in this region. The point is this: here your function is non-analytic about this point, and that singularity is not isolated one, rather it is a non-isolated sort of singularity. So probably this is an answer that things are different compared to this thing. I'm just trying to give a you can say a wild guess sort of thing. Even I'm not very sure, but what I can believe is ki your initial assertion was that I was having a single valued function, and while I was having some isolated singularities, what I was doing, I was creating some kind of slit here, and this slit construction was in order to circumvent these poles. But understand, while I was moving all through from here to here, your structure of the function does not change while I move along. But here you can see your structure of the function would change. Is that clear? Because now your function is no longer a single valued function, rather it is a multi-valued function. So while I move here and again come back after one complete revolution, your structure would change. Indeed, you can say that I'm not on the very same point. So at least this would be there. Del would be there, and limit del tends to 0 also. But overall, your function would, the definition to function, or you can say the structure of the function would change after one complete revolution. Here, the problem is if we are saying my function fz is here, here also it remains fz, and after revolving also, it will remain fz only, because here you don't have such kind of things. So for example, after one complete revolution, e की power iota 2 pi, even if I multiply e की power iota 2 pi, it will remain 1 only. Problems would be created if I have this sort of power. Now I cannot write that this is 1. This is not 1. Is that clear? Because this p minus 1 can be like, it can be
Yes, sir.
between 0 to 1 or something. I mean, if I'm just giving you an answer, I mean, I also know that I'm not giving the right, probably not the right answer, but it's not even the wrong answer, because see, here you are encountering some non-isolated singularity, and here we were discussing some isolated singularities. Okay. So this is what I am trying to explain.
Yes,
Okay.
sir. It's because of that.
Because the branch point is here, and because the function is such, because it is multi-valued function. Okay. So even as I
Right.
introduce a branch cut, but the value after rotation would eventually, uh, like this kind of argument, like for one complete revolution, e की power iota 2 pi would give me 1 only. But if I had a power, let's say p minus 1, or if I had some logarithm here, if I had some logarithm here, so you can see that after one complete revolution, it will be ln z plus iota 2 pi. So your function structure would change. This is what I can say. Is that clear? So that is why I could not cut this particular part. So I could not say कि AB का integral and GH का integral are one and the same thing. Okay, is that clear? आगे बढ़े. Mostly,
Yes, sir.
mostly it would have to do, it would be to do with something like, probably because of the presence of the non-isolated singularities. Branch points are in general non-isolated singularities. Okay.
Yes.
Okay. So let us move ahead and see a few more questions. Question of the type, let's say, yesterday we were doing Fresnel integrals, and while evaluating Fresnel integrals, we were saying that we have to go about a certain contour, and that contour happened to be, that contour happened to be, I will write here. So that contour happened to be what? A semi arc which is inclined at an angle pi by 4. So yesterday we were doing some Fresnel integrals. If you remember, and I told them you will encounter these kind of integrals while doing diffraction, not Fresnel diffraction theory. So mostly there, so therefore it derives its name called as Fresnel integrals. And we found that these values are equals to root over pi upon, I think, 2 root 2, if I'm not wrong, you can just see. So these were the topic of discussion yesterday. So you had to create a certain special kind of arc only. And this is what I told you, that this is what mostly books do. That is what I'm doing also. So probably it would have been a rigorous thing for mathematicians to do, and probably they would have um, ended up saying that this is an appropriate arc. So somewhere you have to remember some things also, and likely so there is another integral that I want to introduce to you, and that integration is integral 0 to infinite dx upon x cube plus 1. So if this is an integral, then how to go about this particular integration? Okay, so how to go about this particular integration? So in order to go about this particular integration, what I would do is I would simply do one thing. I will take this arc. So there are few special contours, you can just remember them so that it helps you in your exam also, because these questions, if they come, it is expected that you should be remembering them, because otherwise you will not be able to do them directly in the exam. So, okay. So here you will have this kind of contour. So I'm making a contour. Now this contour is again oriented anti-clockwise and angled at 2 pi over 3. This is a positively oriented contour subtending an angle 2 pi by 3 at the center. Okay, so let's say this is your O, this is your, let's say, A, then let's say this is your B, and okay. So along OA, you can clearly see yesterday, if I replace this integration by this integration along contour C, I'll write this as C or gamma, uh, dz upon z cube plus 1. Okay. Also, we can see that the singularity is to this will be equals to z cube is equal to minus 1. Is that clear? Z cube equals to minus 1, and let's say this radius is r, and eventually we'll say r tends to infinity. Okay, eventually we'll say that R tends to infinity. So z cube equals to 1 implies z equals to minus 1 raised to power 1 over 3. And this will give you e की power iota, I think 2n plus 1 pi upon 3. Is that clear? So what all singularities will be there? One singularity will be equal to what? E की power iota pi. So I'll write it here. One singularity will be e की power iota pi. One singularity will be e की power iota n equal to 1 रखेंगे तो कितना आएगा? Iota pi हो जाएगा. n equal to 0 रखेंगे तो e की power iota pi by 3. And n equals to 2 रखेंगे तो e की power iota 5 pi by 3. Okay? Is that clear? So you can clearly see e की power iota pi will lie on the negative side of x-axis. So this is not there. E की power iota 5 pi by 3 will lie here. So it is not there. Only one singularity will lie, that is e की power iota pi by 3. So in order to evaluate this integral, the answer would be equals to 2 pi iota into residue of function at z equals to, I think, e की power iota pi by 3. Is that clear? So I would simply say limit z tends to, let's say, write it as z1, and this will be equals to 1 upon z cube plus 1. So clearly this is some quotient of two function fz upon gz, and gz goes 0 as z tends to z1. So I would do nothing, but I would just differentiate the denominator as prescribed earlier, and this will give you this. And this will be equals to 3, and z square will be equals to e की power iota 2 pi by 3. Okay, so this is it. So here you have the value 1 upon 3 e की power iota 2 pi by 3. So e की power iota 2 pi by 3, I will write e की power minus iota 2 pi by 3. And it's easy to see that this will be equals to cos 2 pi by 3. And I think minus iota sine 2 pi by 3. And this will give you, I think, cos 2 pi by 3 is, the cos 2 pi by 3 is pi minus pi by 3 equal to pi minus pi by 3. So it will give you answer 1 upon 3. And cos is negative, so it will give you minus 1 upon 2, and pi minus, I think this will be minus iota 2 to. Okay, so this is what you get, and this all multiplied 2 pi iota times. So on the left hand side, your integral looks like 2 pi iota into, I think this by 3 minus 1 upon 2, then minus iota root 3 upon 2. And this minus 2 gets cancelled, so minus pi iota upon 3. And I think you're left with 1 plus. So you take a negative common out, 2 gets cancelled. So you have pi iota upon 3, 1 plus iota. Is that clear? Okay. So I was discussing this integral. In order to evaluate this integral, I've replaced this integral by this contour integral and took a special contour. So you have to remember this sort of contour here. Okay. And in this special contour, you can clearly see that only one singularity lies, that is e की power iota pi by 3. All other singularities are not inside the thing. So this e की power iota pi by 3 would be somewhere here. So it would be somewhere here. Okay. Okay. So otherwise, all the other singularities are not enclosed inside the contour. So I'm not interested in finding residues about them. So I'm interested in only finding the residue what e की power iota pi by 3. So I've evaluated this integral by finding the residue at e की power iota pi by 3. And what will be the value of this thing? This thing would be equals to what? So this thing would be, I would write this I already have written. On the left hand side, I'm writing it as I. So I would be equals to what? I would be equals to integral along OA, integral along AB, and integral along BO. Understand my point that integral along OA, your Z will be X. Integral along BO. So while you move along BO, what is changing? Your radius is changing. And any point on this line can be written as R into e की power iota 2 pi by 3. Yesterday also we did the same. Today also we are doing the same. And R varies from capital R to 0. So this is, here I can write my Z is equals to what? R e की power iota 2 pi by 3. Is that clear? So this is one integral, this is another integral, and I'm interested in finding what will be the value of this integral as R tends to infinity. I'm interested in finding what will be the value of integration AB as R tends to infinity. So what will be the value of integration AB as R tends to infinity? That I'm going to write here. And understand what is AB. Okay. So along AB, you can clearly see your theta varies. Okay, your theta varies from 0 to 2 pi by 3, and any point on this would be written as, can be written as r into e to power iota theta. Is that clear? And we have to evaluate this integration as r tends to infinity. So let's see what will be the value of this integration. So here I'll write 0 to 2 pi by 3. And what I would write, I think the integration is, just a minute, I think that is dx upon 1 plus z cube. So for time being, I'm writing it here. And I'm evaluating this integration over this r, that is e cube, as z is equal to r e cube. Z is equal to r e to power iota theta. So here you will get r e to power iota theta d theta, and you have an iota here. And then 1 plus r cube e to power iota theta, an integral from 0 to 2 pi upon 3. And let's see what is the integral. So just take a modulus here. So instead of this modulus, this will be less than equal to modulus this. And yesterday, after doing so many questions, I hope you will be able to understand this will be less than 1 minus of r cube. Okay, and integration from 0 to 2 pi by 3, and this is d theta. So this will give you some 2 pi by 3. So this will be less than 2 pi upon 3. There will be some r, and there will be some 1 minus r cube. And as r tends to infinite, you can clearly see that your denominator dominates, because here your power is r cube, here your power is r. So overall, this term will go 0. So the integration along AB as r tends to infinity is 0. Okay, so now you are left with only two things, that is this and this. And on the left hand side, I have already evaluated the integral. Here it is. Okay, so let us find what along OA. So I will write along OA. What is the integral? Integral is simply 0 to infinite dx upon 1 plus, I think, x cube. Along this thing, it will be infinity to 0 e to power iota 2 pi by 3 dr. Sorry, take it dr. And then you have 1 plus r e to power iota 2 pi by 3. And I think you should have also have cubed it. So I think this will become this. Is that clear? And you can clearly see that this is equals to what? This is equals to, if I'm not wrong, this is equals to this minus pi iota upon 3. And you have 1 plus iota root 3. So I'll write here, this is equals to minus pi iota upon pi iota upon 3, and here you have 1 plus iota root 3. Okay, and you can clearly see that this e to power iota 2 pi is 1. So I will simply write e to power iota 2 pi as 1 only. So here you have integral 0 to infinite, and this is dx upon 1 plus x cube, and you have minus e to power iota 2 pi upon 3, and integration 0 to infinite dr upon 1 plus r cube. Whether you write dr upon 1 plus r cube 0 to infinite, you write 0 to infinite dx upon 1 plus x cube, they mean one and the same thing. So integral on the right hand side, I'm now writing on the left hand side, that is integration from 0 to infinite, your dx upon 1 plus x cube is nothing but it is equals to minus pi iota upon 3, 1 plus iota root over 3 divided by 1 minus of e to power iota 2 pi by 3. Oh, why did I write it? I should have not written it here. So that would have eased my problem. Okay, चलो कोई बात नहीं. अब कर दिया तो कर दिया. You cannot help it. But otherwise, if you have not written this, things would have become easy for me. Okay, so I evaluated this integral and what it was. So if I leave it here only, so this was my integral, right? So I'll take this. So 1 upon 3 e to power minus 2 pi iota by 3. So what is your numerator? Instead of this, I would prefer writing this. Okay, so instead of, is that clear? भरत समझ में आ रहा है कि it's not, नहीं समझ में आ रहा. So I'll simply write 1 upon 3 e to power minus iota to power 3. Simply this only, because it's not a good idea to solve it. Although I solved it here, but even if I if I let it be, I have certain things that I can do here. So probably what I can do is, Okay, so I'm not left with much here also. कोई बात नहीं, we're not left with much here also. I thought there would be something that I could do, but okay. This into 2 pi iota also, sorry. कोई बात नहीं, चलो. So I just said to 2 pi iota. Okay. So I thought I would be saved by something, but I'm not saved. I will have to do it. So it is 2 pi
सर
iota. हाँ बेटा बोलो.
सर डिनोमिनेटर वाली टर्म कैसे है? एक बार मैंने मिस कर दिया सर, एक बता।
देखो इस वाले टर्म को ऐसे लिखो, 0 to infinity. ये देखो dr अपॉन 1 + r³ लिखो, चाहे dx अपॉन 1 + x³ लिखो, लिमिट्स तो सेम है. दिस इज 1 + x³. आगे वाले में से 1 कॉमन आएगा, पीछे वाले में से क्या कॉमन आएगा? e की पावर माइनस e की पावर आयोटा 2 pi/3 माइनस e की पावर आयोटा 2 pi/3. इसको उठा के पुट इन द डिनोमिनेटर साइड हियर. दिस एंटायर थिंग गो टुवर्ड्स डिनोमिनेटर, इज इट?
ओके सर, ओके, क्लियर सर।
This is what I was telling. So I was not interested, but I thought I could do some manipulation because I thought I can write it in sine or cosine. But the problem is this. This is not what I wanted. Uh, so what I can do is probably I should try, but again this will remain in any case. So कोई बात नहीं, अब कर दिया तो कर दिया. So I would do is one. I would do, I would just place it uh, in the denominator. So this will give me e की power iota. ये 1 upon e की power iota 2 pi/3 minus e की power iota 4 pi/3. Okay, so it is not giving me much. Okay. I thought it will be some help to me, but it is not. So it's not helping me anyway. So let us get back. Okay, let it be. चलो देखते हैं. So now just find me the values of e की power iota 2 pi/3. So it will give me 2 pi iota upon 3, and you're having 1 upon e की power iota 2 pi/3 is what? E की power iota 2 pi/3 would be, I think I've already written, it will be equals to um, cos, चलो लिख ही लेते हैं. Cos 2 pi/3 plus iota sin 2 pi/3 minus, and you have this is cos 4 pi/3 minus iota sin 4 pi/3. Is that clear? Then this minus because minus bahar ki taraf रखा हुआ है. Okay, so you are left with only a few things now, and things will be done. So integral on the left hand side, integral on the left hand side where we are interested is 0 to infinity dx upon 1 plus x cube. This is 2 pi iota upon 3, and this is I think 2 pi/3 minus cos pi/3. So cos 2 pi/3 is I think cos pi minus pi/3, cos pi minus pi/3 is cos pi by minus pi, cos pi/3 and minus half I think. And this is cos pi plus pi/3. Cos pi plus pi/3 is again minus. So minus minus plus. So this gets cancelled. Forget it. You're left with iota. Sine 2 pi/3 is I think root over 3/2. And sine this thing 4 pi/3 will be minus. So this will add. So root 3/2. So it's fairly easy to see. You can do it on your own also. I think this will be 2 here. So it is only root 3 here. Iota gets cancelled. So you're left with 2 pi upon 3 root over 3. So your integration 0 to infinite dx upon 1 plus x cube can be written as 2 pi upon 3 root 3. Is that clear?
यस सर।
Okay. So this is what I had to tell. Yesterday we did Fresnel integrals where we took a very special contour which was inclined at an angle pi/4. Here we again took a special integral which was inclined at an angle 2 pi/3. So you may ask that where these questions may come. I would say in probably just these questions may pop up. Otherwise, in net examination, you're just going to find questions which are only where you will be only required to find the residues and multiplied by 2 pi iota, and probably a check may be on the whether the contour is anti-clockwise oriented or clockwise oriented, that you have to see. But such rigorous kind of questions may only be asked in examination where you have some subjective kind of approach, or probably inside TFR interview somewhere. But otherwise, these questions that I'm doing right now, like from last 2 classes, you just maintain a copy and just jot them down in the way I'm teaching you. Let's say if I encounter branch point, then you have to remember this sort of integral. and then further what to do and all these things. Okay, are you getting my point? Because these questions are not going to be asked in your net examination for sure. Because you see, already this entire question took me around 30 minutes to 30 minutes to solve, but only 15 to 20 minutes to solve, even when I have done it quite many times. So such questions don't stand a chance in at least those examination where you do not have that amount of time. So probably subjective exams you have time, or otherwise if you are teaching somewhere, so it may help you in your value addition. Is that clear?
Yes, sir.
So we'll meet in the next class, and let's see how things progresses, because today I want to finish it off anywhere. Okay, to finish it off anyway. So today there are three classes. This is the first. Second class will be followed, and then there will be third class. Okay. Is there any doubt you may ask, if you want to ask, because there is still a minute left.
सर इसमें जो हमने कंटूर के अंदर पोल्स लिए जिसमें पाई बाय 3 कंसीडर किया बस.
हम्म क्योंकि देखो e की पर आयोटा पाई कहाँ लाया करेंगे इधर. सो इट इज नॉट इनसाइड द कॉन्टूर. e की पर आयोटा पाई क्या होता है -1. e की पर आयोटा 5 पाई बाय 3 थर्ड कोडेंट में चला जाएगा. सो दीज टू विल नॉट लाई. ओनली दिस विल
तो
लाई.
सर इनके अलावा जैसे 2 पाई प्लस पाई बाय 3 है, 7 पाई बाय 3 और जो और
ओके,
पोल्स
सो वो
रहेंगे
तो
वो
यहीं
भी
पे आएगा ना बेटा. 2 पाई प्लस पाई बाय 3 अगेन इट विल कम बैक
अब
टू द
वैल्यू
सेम.
सेम रहेगी.
वैल्यू सेम
यस
रहेंगे.
यस.
और यहाँ पर इट इज एक्स क्यूब. इट इज नॉट एक्स की पावर 1/3 और समथिंग. लाइक दिस इज
राइट
completely.
राइट राइट.
So you have no issue. You will not have any sort of issue.
ओके सर ओके.
Okay. So I hope it is clear. So I will resume in the next session.